All right, in the interest of starting our review for the midterm coming up in a couple of weeks, I'm going to be going over this question, which was relevant to our learning objectives from last week with momentum conservation. I'm recording this and going to upload it to YouTube, so if you prefer to just watch this later, feel free to do so if you're right in the middle of completing your lab work. It says a wooden block moves along a horizontal frictionless surface, as shown in figure 2.1. We've got the block has a mass of 85 grams and moves to the left with a velocity of 2.0 meters per second. A steel ball of mass 4.0 grams is fired to the right. The steel ball, moving horizontally with a speed of 45 meters per second, collides with the block and remains embedded in it. After the collision, the block and steel ball both have speed v. So it's similar to the ballistic pendulum, except for this time our target is, also has some momentum it's contributing. It's not stationary. So first it asks us to calculate v. This is clearly a conservation of momentum type problem. And so I'll start with that idea that the initial momentum is equal to the final momentum. Remember that the total momentum for a system of objects is constant, or the sum of the individual momenta of the objects before the collision is equal to the sum of the individual momenta of the objects after the collision. But after our collision, we only have one object, right? Because the steel ball remains embedded inside of the block there. So keep that in mind, how that will look sort of mathematically. The initial momentum, I'll start with the steel ball, is going to be, the mass of the steel ball, called object 1, times its initial velocity, and we'll add to it the momentum of object 2, so mass 2 plus initial velocity 2, and that's going to equal an object that's equal in mass to the sum of the individual masses traveling at a shared speed v. Substituting in values, I've got 0.004 kilograms, right? 4 grams is 0.004 kilograms, traveling at a speed of 45 meters per second. Plus object 2 has a mass of 0.085 kilograms, and it's going at a speed of a velocity of -2 meters per second, right? We have to make this negative because we've assigned right as the positive direction. That's equal to the sum of the masses. So 4 plus 85 is 89 grams, or 0.089 kilograms. And then the shared speed v is what we want to solve for here. Working through this, we get 0.004 times 45 means that there is 0.18 kilogram meters per second of momentum from object 1, the steel ball. 0.085 kilograms times -2 meters per second is -0.17 kilogram meters per second. Again, the negative sign indicates the vector here of momentum. And so when I add those two, I get 0.01 kilogram meters per second. Because this thing is going slower, but it's a lot more massive, it actually almost has as much momentum as the steel ball, which is going much faster, but less inertia there. So the total momentum is only 0.01 kilogram meters per second. The momentum of this in this direction cancels out a lot of the momentum here. So that new object, 89 grams or 0.089 kilograms, we divide each side of this equation by 0.089 kilograms, and we'd be left with meters per second. So that's on the left side divided by 0.089, and I solve for my velocity of my steel ball block object, 0.11 meters per second. The question goes on to read, for the block and ball, state the relative speed of approach before the collision. So those of you that prefer to sort of deal with inelastic and elastic collisions by considering the kinetic energy, I suppose you could, do that here, but it's really asking you about the relative speed. So it is important that you know how to calculate relative speed. The relative speed of approach, remember, is how fast do these two objects see each other. They're traveling in opposite directions. So the rule is we add their speeds to calculate the relative speed. So this one's going 45, this one's going 2, but they're going opposite directions. And so the relative speed of approach is 47 meters per second. They see each other at 47 meters per second. After the collision, they are one object. And so what is the speed of separation between an object connected to itself? 0. Okay, it's like they aren't separating at all. And so here we can clearly see that the relative speed of approach does not equal the relative speed of separation. So we can use the answer here to state and explain whether the collision is elastic or inelastic. Make sure you're answering it first, or eventually inelastic, because the relative speed of approach does not equal the relative speed of separation. The final 2 marks in this paper are from the question, use Newton's third law to explain the relationship between the rate of change of momentum of the ball and the rate of change of momentum of the block during the collision. So here I would first, maybe state Newton's third law that says forces between objects exist in pairs, equal in magnitude, opposite in direction. Here the 2 objects are the steel ball and the block. Because force is the rate of change of momentum, and because forces exist in pairs, we can say that the rate of change of momentum of the ball is equal to the rate of change of momentum of the block, right? Because the forces are equal, and force is the rate of change of momentum. So you kind of want to put that into your own words for the final 2 marks on this paper. This comes from ACE Physics Syllabus Code 9702, paper 21 from October-November 2018. This has been question 2. Dr. Schleif signing off.